That's good.
Okay, great. So thanks everyone for joining today. So it's our pleasure to have Nicholas, Samuel, and Cong, which are gonna present the AutoML Decathlon, which was held at NeurIPS last year. So, and yeah, they're basically gonna speak about their insights that they got from this application of different AutoML methods on diverse tasks, which are not that mainstream like computer vision or NLP. So yeah, I'm really excited to hear them about their findings. So, and the floor is all yours, guys.
Cool. Thank you so much for the intro. Yeah, so let's get started here. So, here we go. Here's kind of an overview of the talk. So first, I'm going to present about kind of the diverse tasks problem in AutoML and how this kind of differs from the usual kind of evaluation in AutoML and other things like neural architecture search. And then Sam is going to take it from there and kind of dive deeper into the actual competition and how we designed it and things like that. And then things like how we encourage participation by like having hackathons and stuff like that. And then we're going to talk about the two different phases of the competition. So the development phase, in which people developed their methods on a set of 10 diverse tasks, and then the test phase, in which we evaluated the participants' methods on a held out set of 10 diverse tasks. And Cong will talk about that part. So yeah, let's get started. So again, I'm going to be talking about AutoML for diverse tasks here. So yeah, I think hopefully most of us are familiar with the ImageNet story. So ImageNet is a kind of large data set comprising like 14 million labeled examples with like 1,000 different classes. And it's, of course, images, so it's targeted at computer vision. And you see in this plot on the bottom here that over the course of like 5 years, and now it's been even longer than that, people have developed better and better neural network architectures for this task, right? And so we have like a picture of the GoogleNet architecture here on the other side. And as you can see, this is a pretty complex architecture. It's not clear to me like what all of the design decisions are, how like someone would have come up with this as like a first attempt, right? So clearly a lot of human expertise over the course of several years went into figuring out these tricks for designing architectures like this for computer vision in particular. And kind of the moral of the story that I want to pull from this is that this whole process of collecting the data for ImageNet and then all of the hand design that went into modeling over the course of several years for this problem was both expensive and time consuming. And yeah, I think it should be obvious based on the complexity of the architecture here that this took a lot of time. And of course, because the plot is over the course of 5 years, and now it's like 12 years, 13 years, there's been a lot of human effort that's been put into this. And so what our motivation is instead is to use AutoML as a tool to help to automate the process for emerging tasks that aren't ImageNet scale. And so these are like things I imagine like smaller scale tasks in like the hundreds of, different scientific laboratories at different like university campuses and stuff like that. And so usually these labs have some kind of unique data requirement. They have their own data, et cetera, and they're not ImageNet scale, but there are a lot of these tasks. And it's unlikely that the same kinds of computer vision architectures are just going to work out of the box for these. And we don't want to have to reinvent machine learning every time we have a new task like this. And so we'd like to use AutoML as a tool for scientists. Okay, so before we get into that, let's first kind of dive into the three kind of most important components of the machine learning pipeline. So there are three things here. You need models, you need data, and you need hardware. So we're going to immediately cross out hardware because you can just get that from AWS or something. So we're going to mainly focus on models here, but I'm also highlighting data because that's another thing that I'm interested in. So choosing models requires machine learning expertise, as we learned from the ImageNet example. And as for data, creating large labeled data sets is expensive, which we also learned from ImageNet. So for these non-machine learning experts that might be experts in other scientific domains, constructing models and curating data is quite expensive and difficult. And I've included a couple of fake quotes here from what I imagine a scientist might say about this. How would I pick, which model to use without, a bunch of machine learning PhD students helping me? Or, I don't have enough labeled data. How can I still use machine learning? So we actually have solutions to these with AutoML, or things that are building towards solutions to these. We'd like to automate these two processes. So for modeling, I think a typical answer to this is to use something called Neural Architecture Search, which since you're at the AutoML seminar, I'm sure we're all familiar with this. And then as for the data side, there are tons of things you can try, like transfer learning, fine-tuning, or using weak supervision. And again, we're going to focus more on the modeling side here. So all of that to say, we need to return to the original question. So what exactly is AutoML for diverse tasks? So because it is a subfield of AutoML, of course, as the name suggests, we're trying to automate machine learning pipelines. And we additionally have this motivation of wanting to reduce the need for machine learning expertise in the use of these techniques. And in the best case, the goal would be to make machine learning more accessible to non-ML experts who are experts in other domains. And so hence the diverse tasks part of the name. And so a big question here and an opportunity that AutoML for diverse tasks poses is the question of whether or not AutoML actually tends to do this in practice. So who actually tends to benefit from developments in AutoML and neural architecture search? So the reality is that a lot of developments have been focused on computer vision and NLP. And these are domains where there's been already like a ton of expert hand design of, for instance, neural network architectures for vision. And so while things like NAS do promise improvements in those domains, the improvements are tend to be kind of marginal compared to the already state-of-the-art hand design networks, whereas the potential for benefit for like other domains where there really hasn't been a lot of hand design is really huge. And so there's really a lot of promise there. And so the argument for AutoML for diverse tasks is that we should really refocus the attention to these hundreds of thousands of diverse domains out there that could really truly benefit from this. So just to reiterate that, mostly machine learning people tend to benefit from AutoML. And we want to change that. We want to make people in the sciences and other domains, we want to help them to benefit from AutoML as well. And so in other words, we want to make machine learning more accessible. And so again, we want to design AutoML methods that are aimed at diverse tasks. And with that said, I will pass it over to Sam. I think we'll probably have to switch screens here. So we'll stop sharing and Sam can pull it up.
All right, thank you, Nick. Does this look good to everyone? Here. Okay, then I'll jump into talking about the competition setup and the first main phase of the competition. So the competition was divided into two phases, the development phase and the evaluation phase. And in the development phase, we released 10 public data sets, and each team developed their own approach, made submissions, and got feedback on their performance for each task. And we used a metric called area under performance profile to rank all of our submissions on a public leaderboard, and more on that later. So the development tasks are representative of, but distinct from, the final set of additional 10 test tasks in the evaluation phase. Competitors had access to development tasks, but the test tasks remained private for the duration. And then in the evaluation phase, the final submission from every team was tested on these 10 private data sets and evaluated on its capability to adapt to these unseen tasks. And finally, the results of our performance profile-based evaluation determined the winner of the competition, who received a $15,000 grand prize. Okay, so now more about this development phase. So as Nick mentioned, we really wanted this competition and the methods developed for it to tackle this problem of AutoML for diverse tasks, beyond just the classically targeted domains like vision and language. So our data sets, of course, needed to reflect that goal. This entailed diversity in things like domain and also task characteristics, such as data shapes or prediction target type. And as a starting point, we sourced some data sets from NAS Bench 360, which, as the name suggests, is an existing benchmark for NAS and AutoML methods. And shown here is a table of the 10 development phase tasks. And you can see they vary in their domain, including images, financial time series, audio, and the natural sciences. And they represent a broad spectrum of practical applications in scientific, technological, and industrial areas. They also differ in things like sample counts, dimensionality, and problem types, including regression, single label and multi-label classifications. So we were able to meet this goal of task diversity well, we think, across multiple different axes. And we encouraged, at the beginning of the competition, we encouraged the participants to consider a wide range of different approaches, including but not limited to, traditional hyperparameter optimization, ensembling methods, and modern techniques like NAS transfer learning even. So with these multiple heterogeneous tasks, we needed an aggregate metric for ranking purposes. Our metric used for evaluation was based on performance profiles. So with performance profiles, you take all the individual task metrics for a given method and plot a curve of how often the method's performance is within some variable factor of the optimal across all the methods. Like so in this example graph, the factor tau on the x-axis and the proportion on the y. And our metric is simply the area under this performance profile curve, also known as the AUP. So why do we use this AUP score? Why do we devise this new score as opposed to some, more traditional like aggregate ranking methods? So the important quality of performance profiles and AUP is that they take into account how close a method is to being the best at each task instead of just a relative rank. So something like average rank, which was commonly used previously, loses in this information and may unfairly penalize methods that are actually strong. So for example, if a specific task is a bit more easy and many methods have close and really good scores, number 10 may actually be very similar in performance to like number 1, but its average rank will suffer quite a bit, whereas AUP will address this issue and not penalize it as harshly. So with our competition setup of data sets and scoring established, next there's the matter of how the participants will actually interface with the competition. So we provided them a starter kit of code to help them download the data and begin experiments with a tutorial and a Docker image. Some simple baselines were also included as easy examples for them to look at and learn from. So their implementations needed to complete three main things. So the model initialization, the model training, and the model testing methods. So to gauge their progress, they could also run either a quick local evaluation or submit to the official competition page for evaluation on the true holdout sets. Our overall development pipeline was based on that of a past AutoDL competition, mainly the training and testing structures mentioned before. So one important consideration was the standardization of the data format, because again, we had very heterogeneous tasks. We needed an easy way for participants' code to ingest them. So we made all the tasks a standard, batch time, channel height, width shape. And if a task is originally lacking one of these dimensions, for example, a 1D sequence task wouldn't have both spatial dimensions, then the originally missing dimension would just be set to 1 to indicate this. So what's important is that the participants develop methods should see this necessary metadata like the input-output shape, but be agnostic to the exact task and the details of it like its domain. And to that end, we considered a potential development dataset anonymization in pursuit of more generalized, task-agnostic development. For example, hiding task names or even slightly altering the data itself, for example, with noise injection. Ultimately, though, we concluded that this wasn't really feasible or necessary, mainly because, a lot of these data sets are, publicly available. Participants could look them up if they really wanted to. However, overfitting to development will be a detriment to the final evaluation performance. And we were checking code during the evaluation stage to make sure there wasn't any explicit overfitting based on external knowledge. Okay, so next I'll talk a little bit about the hackathons we organized to support the main competition. So with the main goal of introducing, university students at all levels to AutoML, AutoML and diverse tasks and its challenges, and giving them initial exposure to this competition, we hosted 3 separate hackathons at Carnegie Mellon, Wisconsin-Madison, and the AutoML Fall School in Freiburg. So these hackathons were all in person and they took place during consecutive weeks last year. And we provided notebooks that would make it easy for them to set up a smaller scale version of the competition and the data and get them pointed in some promising initial directions that they could explore. So to incentivize some deeper engagement, we offered several prizes to the participants. So teams could either present on methods they tried to implement or that they researched and thought were interesting. And they also could present at the end on these. And they also could submit to the actual competition if they so wish to. And they would get an additional prize for beating our best performing baseline. And of course, there's the incentive of the grand prize as well. So here are some of the participants at our hackathons. There's Nick with the Team Pure Leaf at Wisconsin. 2 CMU teams who both presented. And 2 teams from the Fall School. And here's just, we're showing the final standings after our development phase. And this leaderboard shows quite a good level of engagement from the community, which we're very happy with. And there's many notable teams that consistently were tuning their methods and surpassed the baseline. And a few of these leading entries were actually from hackathon participants, which was really great to see. So with that, I'll pass it to Cong to cover the test phase and competition results.
Okay, thanks. Let me share. Can you see my screen well? Okay. So while the competition was going on for the first phase, the organizers were busy choosing the test data sets. So we need to make sure that the test data chosen should be representative of the development data sets. That basically means we should still cover a lot of domains, have variations in terms of number of data samples, input shapes, data types, and also different evaluation metrics. That is basically the same goal for diversity for this competition. So we decided to make sure that the test datasets have a loose correspondence between the dev test. For example, there was our cribbled dataset in the dev test. So we aimed for a stock to match actually the cribbled datasets. And we researched existing machine learning in particular domains to actually target datasets. So here is a list of test dataset that we ended up choosing. As you can see, the chosen dataset is diverse in domains, including images, serial data, audio data, and also PDE and computational biology. It also varies in input dimension, output dimension. The size ranges from anywhere from 100 kilobyte to several gigabyte. And we also use the various evaluation metrics for these data sets. So during the evaluation process, we ran into a code bug on the final day of the competition. So we decided to request manual final submission from these teams. And also it doubled as a debugging period for these final submissions. In the debugging process, we needed to solve the method's small errors on some of test data set. For example, some of the file path discrepancies. And also we send out log files to the participants, but asking them to update their submission, but without giving any hints of the test task. So in the service of fixing minor code issues, we specifically stated that this is just a purely opportunity to solve these errors. So no major changes should be allowed. And they could not add any new files or implement any new functions in the updated submission. So once we receive the updated submission, we manually check the participants' update, make sure they follow the rules, and spend some time debugging on our end, fix some minor issues, including like numeric problems and fixing some typos, so that all the updated submission we receive actually ran on all tested tasks successfully. So in the final leaderboard, 9 teams ended up beating the most strong performing baseline, which is XGBoost. In the leaderboard, we observed the top performers are roughly consistent from the dev leaderboard to the task leaderboard, with some minor changes in rankings. For example, Team TrueFit was number 5 on the dev task, but it ended up with winning the competition. We observed a lot of diverse methods were used in the competition, including traditional deep learning methods, convolutional neural nets, recurrent neural nets, and transformers. And transformer learning with pre-trained models were also used. Of course, a lot of ensembling methods, including provided XGBoost, improved version of XGBoost, and lighter GBM were included in some submissions. And it's happy to see that the NAS-based approach were also used by the second winning by the team that ranked second in the final leaderboard. And many teams choose to combine a lot of these deep learning and traditional machine learning methods with hyperparameter tuning and added customized optimizers. So the submission made the computation diverse in task, methods, and also in compute times. As you can see in the figure below, there's a huge variation across teams and also cross tasks in terms of compute time. So in the computation, some team would choose to infer the data type from input shape. As Sam mentioned, we have standardized the data input shape, so it provides opportunity for the participant to actually infer the data type from the shape. And based on the inferred data type, some team would actually choose to build a decision tree to select models. For example, there's the team from University of Paris. They would choose the simple IN for time series data. For tabular data, they would actually run both XGBoost and the RNN and chose the better performing one. For video and image, they chose customized architecture from literature and the fallback to XGBoost or white resonant for other type of data. But there are varying strategy preferences from other teams. So for example, the CMU team, which ranked first in dev and fourth in final leaderboard, they built a different decision tree. So in their decision tree, both white resonant 1D and 2D were used, and GRU and the Cong GRU were also used, depending on the type of data they inferred. So the Freyberg AutoML lab combined the inferred domains model selection together with transfer learning. For example, they chose pre-trained UNet for segmentation, RegNet or pre-trained RegNet or white resonant for image classification. They also combine the transfer learning with bags of tricks. For example, they use learning rate finder instead of hyperparameter tuning, which they found to work better. They implement early stopping, not only to prevent the model from overfitting, but also to reduce the search time. Yeah, as I mentioned, hyperparameter tuning were used by a lot of teams. So some team chose to further optimize the hyperparameter search. One team chose to use the technique invented by the Microsoft researchers back in 2020. They would random directory search with the technique use adaptive step size with random sorting. So this approach begins with low cost initial point and gradually move to the high cost region only if necessary. So in theory, this approach applies to general box functions. It turned out it worked better for XGBoost in practice. So in two of the dev tasks, Crypto and Ember, which is tabular data sets, comparing XGBoost without the optimization with XGBoost with optimization improved the performance by about 80% on both tasks. NAS approach was also used. Tencent AutoML Lab built their solution based on top of Dash developed by Amit's group. They rank the third in dev leaderboard and the second in the final leaderboard. They added SE attention multi-branch self-dissolution to the white ResNet backbones. Also implemented two-stage search, which is kernel dilation search plus the width search. For these who are not so familiar with Dash, so Dash is a blend of XD and Darts. Both of them are state-of-the-art NAS approaches, and the Dash was proved to have better efficiency compared to both approaches. So finally, the winning team. So the true team is from a solo player. He used to rank number 6 in Kaggle. So in his submission, he combined dozens of tricks, focusing on architecture range, parameter tuning, and efficient experiments. One of the innovation in his submission was he used a transformer with time-based tokenization for both sequencing and the signal data. And he would choose efficient net B0 or B2 for ImageNet classification based on the data dimension and data size. UNet was used for segmentation, and light GBM was included for tabular data. So he sampled hyperparameters from wide yet reasonable distributions with random yet evolutional sampling during the training. So all the model would tune over 6 to 15 cross-validation runs, then followed by the full training. And they found out that including an MLP time series module sometimes helps. So for the time series sequence data, he decided that using vision transformer seemed to be a good idea. So he uses a vision transformer, which can take a 2D input, one dimension being the number of channels, the second dimension being the time steps. He identified many knobs too for the vision transformer, including like learning rate, weight decay, dropout, pulling, position embedding. Sometimes he does recrop, use stop count to increase the search performance. And also, of course, he can tune the time steps per token and the limit that to 12 for the maximum value. So here are the takeaways for the competition. So we observe that all the top methods combine the standard AutoML approaches with a wide range of methods, including traditional deep learning methods, large-scale transfer learning, and many of them fall back to simple ML models for some tasks. And existing methods targeting AutoML for diverse text still perform strongly. In the competition, the more general purpose methods that perform strongly across the task types outperform specialized domain-specific methods. And all top teams open source their solutions on GitHub. Yeah, thank you for attending our seminar. There's a special thanks to our co-organizers and to Amit for leading the effort with us. And there will be a follow-up to the AutoML Decathlon. We'll be hosting another AutoML conference, another AutoML Club associated with AutoML conference. So please stay tuned for details. Thank you. I think Nick, Sam, and I are happy to take any questions.